The last video illustrated the use of geometric shapes in algebra. You can also use geometric shapes in calculus and differential equations. The product rule in calculus states that the derivative of a product is the derivative of the first function times the second plus the first function times the derivative of the second. But we can write that more easily as the derivative of a box times a triangle is the derivative of the box times the triangle plus the box times the derivative of the triangle. Now, this is the same as what we had before, but if you're actually doing complicated problems, sometimes actually putting objects in different geometric shapes can make the calculation easier. The quotient rule in calculus says the derivative of a quotient is the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator squared. But we can write that more easily as box over triangle prime, that is the derivative of box over the triangle, is the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, all divided by the denominator squared. The chain rule in calculus says the derivative of a composition is the derivative of the outer function applied to the inner function times the derivative of the inner function. We can write that more easily as the derivative of f of a box is f prime of the box times box prime. So for instance, if f of x is arctangent of x, then f of a box is arctangent of a box. So if I put sine of x in a box, find the derivative of arctangent of sine of x to be the derivative of the arctangent function, that is 1 over 1 plus the box squared times the derivative of sine of x, or 1 over 1 plus sine squared of x times cosine of x. As an example of a multivariable chain rule problem, consider a function f of u, v, and w, and functions g of x, y, h of x, and m of y. So suppose we compose those functions. Suppose we define p of x, y is f of g of x, y, comma, h of x, comma, m of y. The partial of p with respect to x is going to be the partial of f with respect to u times the partial of u with respect to x plus the partial of v with respect to v times the partial of v with respect to x plus the partial of f with respect to w times the partial of w with respect to x. Now, since h is a function of only one variable, we would write that as an ordinary derivative instead of partial derivative. And since w, which is m of y, is independent of x, that derivative would be 0 because as far as x is concerned, w is a constant. We could also write these in variables. Let's say z be p of x, y, u be g of x, y, v be h of x, and w be m of y. Then the partial of z with respect to x is simply z sub u times u sub x plus z sub v times v sub x plus z sub w times w sub x. When considering partial derivatives of compositions and functions, a tree diagram can be useful, especially in making sure you don't forget one of the components that affects the derivative. If you're interested in seeing this graphically or in how to use LaTeX to create mathematical documents, add a comment below. We can also use geometric shapes in integration. For instance, substitution or U substitution is just an application of the chain rule, and integration by parts is just an application of the product rule.